Okay. Yeah. Thanks everyone for coming and welcome back. I'm Jiahui Zhou, or you can call me Joe. I'm currently assistant professor at Stony Brook. So for the next session, we'll have two invited talks, each of 40 minutes. We'll start with Neil and then Minchu. Are you here? Oh, cool. Yeah, if you have a minute, you can come to Karen. We have some form for you to sign to allow, us to stream your talk. Just got your consent. And while we're doing that on the background, let me briefly introduce Neil. So Neil is a co-founder and chief modeling officer of Kyutai, which is nonprofit AI research lab. If you have heard about Moshi, I remember watching the Moshi release demo, which is a live speech AI release sometime last year, which was very, very impressive. And so he was previously at Google DeepMind, and he started and led a team working on speech generation and audio generation. And before that, Neil spent some time at Facebook AI Research, also working on speech recognition, audio understanding. And in the part-time, he also teach speech processing technologies in ENS in France. So without further ado, let's start the talk. Neil?
Thanks a lot. Thanks a lot for the introduction. I switched to the presentation in full screen now. So I'm very happy to be here today to talk about my favorite topic, which is audio language models. So just a disclaimer, this talk will be more a historic, chronological story of my relation to this field. So it will mostly rely on the work that my team and I did, but obviously it was just a part of a much bigger effort in the community. And for me, the main motivation for working on such a topic was a high-level goal of creating foundation models for generative audio, which is the main topic of this workshop. And what we could call foundation models in that regard was the idea of having models that could exploit massive amounts of unlabeled data in unstructured, easily collected data, and could then be fine-tuned for a wide range of tasks. In the case of audio, typically, tasks could be audio generation or audio understanding, or audio-to-audio transformation. And so there are a ton of ways to train such foundation models, right? But when we look at the main characteristic we expected from such models, namely that they will benefit from a generative pre-training. They should exploit unlabeled data. We would like them to be as generic as possible. For example, for us, it was very important from the beginning to have a framework that could be applied not only to speech, but also to music, to general audio, just, something that had enough generality and not too much prior knowledge about speech. It should model long-term dependencies, complex structure, for example, language that can be learned from speech, musical rules from music, and so on, and allow for zero-shot abilities. And so there is an obvious framework for that, which has had a tremendous success in text, which is language models. So came to us the idea of, okay, can we train a language model for audio? And mainly the main idea is like, how do you train a text-based language model? The main training framework is next token prediction. So you have a stream of text, and based on it, you're going to predict the next word, the next token in a sequence. And the main idea was how to go from this framework to something that will work in audio. So actually, this has been something that has been explored for a while. In particular, there is one challenge that emerges, that when you predict with in the text domain, the information is so compact that you can predict long-term signals with few input sequences, short input sequences, right? Because you have only few characters to make up, for example, a sentence. However, audio is, as you know, a very, very complex signal that is very dense and much sparser in information, for example, than text. And so it's a challenge for that. Yet, as soon as 2016, there was kind of the first audio language model, or one of the first audio language model, in the form of WaveNet. So in that case, in that context, the idea was to train a generative model of audio with next kind of token prediction, instead of predicting a token like you would do for text, you will just predict the next value in a waveform. So it was literally language modeling of a waveform. So now a language model casts its prediction task as a categorical classification task, right? So you typically in text, you predict the next token in a finite vocabulary. So how do you do the same in audio? For example, if you want to predict the next waveform in a categorical fashion, what you can do is simply do scalar quantization. So you take the possible values for your waveform, and you say now that there are only, in the case of a WaveNet, 256 potential value that are set on a specific grid to maximize the usage of your categories. And now you can train a model that predicts waveform as if it was a classification task. And then the question is, how do you model long context, right? Because as we saw, even at 16 kHz, which is not a great quality, you get 16,000 values for a second. So even if you want to model a sentence, it's a lot of values. So they relied on dilated convolutions that are a trick that allows to model very long context with convolutions without exploding the memory and the number of parameters. So it was, I think, very transformative work in the field of text-to-speech. And in the context of generating audio conditioned on text, it was very good. However, it was very slow because of the autoregressive generation in this output space, which is very highly sampled, 16,000 times a second. And at the same time, what was impressive at the time, but still, questioning, was the fact that if you trained the model with text conditioning, you get state-of-the-art text-to-speech. But now if you train it without conditioning, so you just train it in a purely unsupervised fashion, the same way you would do with a language model, well, you see that the model is going to learn. Maybe I'll let you listen and then I comment.
Just even. Det visses hos låter verkligen inte förtjänad. Både nej kunde jag favorite. Jag tror att jag heter det den arta dig. That clear what han. Just even.
So in a way, there is very high naturalness, right? The audio sounds pretty good, in particular for 2016. You have very natural non-speech sounds from the mouth and so on, but the language is just not there, right? So it was a very strong sign that you could learn a lot of characteristics of speech in a purely unsupervised fashion, yet it was not enough to learn the underlying linguistic structure. And so how would you learn such structure? Ideally, instead of predicting directly in the waveform space, you would rather have something that is a bit akin to pseudo characters, right? And what do we mean by that? The main idea will be that you would want something that is low frame rate, okay? Because you don't want to do too many steps of generation. You want something that is very compact like text. At the same time, you want the semantic information to be captured, which is the thing that was lacking in the previous audio. Yet you also want these units to reconstruct high quality audio. And then the nice thing is that you would then represent, instead of predicting directly in the audio domain, you would project your inputs to this audio domain, to this compact token domain. You would then perform your prediction task into this space that has the right characteristic, and then you would convert these tokens back to audio. And in particular, several groups, including the group of Emmanuel Dupuy at Facebook, made a very seminal line of work in that regard called Textless NLP. And here the idea was that instead of predicting audio in the waveform domain, you would extract this pseudo text that I described right before. And the way you would do it is the following. You would train a model for a mask, typically mask prediction tasks, but there are also other tasks like contrastive and so on, but mostly representation learning tasks on audio features. And then when you have trained this model for a high-level representation learning task, for example, mass language modeling, what you can do is project an audio through a part of this architecture, take some of the inner layers from it, run a K-mean algorithm to go from continuous valued embeddings to discrete categories. And now you have your units. So now your audio representation is a quantization of a high-level representation of speech, which is at a much lower frame rate, hopefully has more semantic information, and could be reconstructed to back to speech. And so now you have these units and you can train a language model for audio production in that space. So I think it was a very transformative work for several reasons. It's completely unsupervised, exactly what we are looking for. Now the frame rate is drastically smaller than it used to be, right? Because, for example, in the context of Hubert, it's 50 hertz. And very, I think for me, when I listened the first time to these demos, I was really mind blown by the fact that for the first time, I could hear a model learn linguistic structure just by listening to audio without having seen any text, hence the Textless NLP name. But I will let you listen to it.
In some parts of the country, where white stones in the lakes are so large that a common liquid flattened all the ground is greater than the top, and the beaches are so white that white stones are black.
So this was very impressive and very inspiring, in particular to my team. But we felt that there was still something that was missing. In particular, so the linguistic structure is there. It's clearly, this part of the problem seems to work quite well. However, the quality part and diversity part is not there. When I said one thing I said in the beginning, that was very important to us to have a model that was not only for speech and would rather be a generic framework for any kind of audio signals. In that case, the tokens were quite speech specific because they would include prosody information and so on and so forth, which are very specific to speech. Moreover, the decoder that goes back from the tokens back to audio, in that context, was speaker specific. So you will need to pass your tokens through a Tacotron 2 model and then a wave glow inverter. So it's quite a heavy process, right? It cannot model arbitrary sounds, not even arbitrary speakers or arbitrary recording conditions. So we have the semantic part that is well captured here, but what is missing is a better handling of what we could call as an acoustic part, which is modeling all the range of diversity of audio in all the voices, the speaking styles, the background noise, the music, and so on and so forth. And so at the same time, we are working on, in my team, on SoundStream, which was, to the best of my knowledge, the first neural codec that could compete with actual audio codecs like Opus. The main idea, and I don't want to go too much into details, but was to train a generative adversarial network where the generator has quantization in its bottleneck. And in that context, the task for the discriminator is to tell whether an audio is a real audio, so uncompressed audio, or a fake audio, which means compressed audio, and such that the generator is trained to generate audio that sounds as closely as possible to non-compressed audio, while we enforce the compression in the bottleneck. And so now you have a purely end-to-end way of training an audio compressor that is computationally much more expensive than Opus, that's for sure. But for the same bit rate, so the same number of tokens, the same memory usage to compress the audio, has a much higher quality. And so here is to give you an idea of the quality of Opus versus SoundStream. So that's Opus at 6 kilobits per second, and now SoundStream. So we thought we had solved the issue at this time, right? Because we had these SoundStream tokens. I'm like, okay, we are just going to replace Hubert with SoundStream, and it's going to be the perfect audio language model, and we'll be done, and we'll work on something else because it will solve the problem, right? The quality is so good, you just pass it to a language model, and you're good to go. So we did that with a lot of enthusiasm, and it kind of worked, but it was also very disappointing. So in particular, we felt in a way that we were back to WaveNet, in the sense that the audio quality was very high. In particular, we observed for the first time zero-shot voice cloning, even before Valley, or even before we published our first work on AudioLM. The very first experiment we did showed perfect voice cloning. Yet, the speech is babbling, so it's a lot of pseudo words, no meaning. You're just going to see. So the beginning is a ground truth prompt, and then it's generated, and you'll see that it goes from something that makes sense to something that is a perfect same speaker, but it's completely meaningless.
And for Annie, outside that, it was as though a dark cloud was confusion. She can of low kind this went also of a doctrine of.
Similarly, we train it on dataset of internal dataset of piano at Google. And again, you're going to clearly see when the model starts generating from a prompt. So it's definitely piano, right? The acoustics are quite good, I would say, but there is no structure at all. So we are back 5 years before, so with something that is very qualitative in terms of acoustic quality, but terrible in terms of high-level structure, which is just non-existent here. And so we decided to take the simplest solution, which is just to combine both approaches. So we combine what we call semantic tokens, which are tokens extracted in the same way as I showed for textless NLP. In our case, it was wave-to-Hubert, but the philosophy is really the same as Hubert. That's going to model the high-level content. And we combine that with acoustic tokens that will come from a SoundStream or any other codec, and that will capture all the finer audio details and rather than the long-term structure. And so the way we would model audio in that fashion is the following. So we would create a statistical dependency between the acoustic token and the semantic token. So the semantic token are going to condition the generation of acoustic token. So we trained a very complex system at the time, now looking back at it, where we had a first model that would predict the next semantic tokens from the past one. So it's just an autoregressive model of semantic tokens, basically very similar to textless NLP. But now, instead of trying to reconstruct audio from semantic tokens that have lost too much information to reconstruct high-quality diverse audio, we use semantic tokens just as a conditioning to a second neural network that produces the acoustic tokens. And these acoustic tokens now become the final output that is reconstructed back to audio. So importantly, we don't use the semantic tokens for the reconstruction here, right? We just get rid of them and they only serve as a conditioning to control the generation of acoustic tokens with a good structure. And now, when we want to generate coherent continuations, for example, we have a 3-second audio prompt.
Some images, like some sensations,
we convert it into semantic tokens and acoustic tokens. We use the prompt in semantic tokens to predict the future semantic tokens. We concatenate all the semantic tokens sequence with the prompt in acoustic tokens, and we generate the future acoustic ones. And then we could reconstruct audio. And this was in 2022. We showed that we had now a general framework for audio continuation with state-of-the-art speaker fidelity, and also for the first time, a model for music continuation that will work very realistically.
Nay, nay, lording, answered Wolf. We know not how to call you lord or lady. We have lived too long in the forest, and are now
for a model that had never seen any text or any partition, we felt we had kind of cracked some things that worked pretty well by combining semantic tokens and acoustic tokens. Yet, for us, this was just a proof of concept of the main technology. Obviously, continuation is an interesting debug task because it allows you to just focus on the generative part. But it's not a task as interesting as, for example, text-to-speech. So in the context of speech, speech generation is kind of the master task, is to be able to specify a text you are interested in and generate it in.
Oh, what a grand thing to happen on a raw day. Oh, what a grand thing to...
So what I just showed before is textless speech generation, right? We go from semantic tokens and we generate acoustic tokens. So what we could do instead is just do one stage of AudioLM where we condition on text instead of semantic tokens, and we predict acoustic tokens. So this was done by a team at Microsoft, and it's a very famous line of work called Valley, and it's exactly that. So it's an audio language model that just conditions directly on a text or phoneme in that case, but does not rely on the fine distinction between semantic and acoustic token. It only predicts acoustic token, but since it has this strong conditioning of text, it works pretty well. However, when we look at the training data, it was trained on LibreLive, so 60,000 hours of data. And in particular, what is interesting with that is this data needs to untangle everything. So let's say you have only trained your text-to-speech on male voices, and now you want it to work on female voices. That means you should acquire new data with labels, so with transcripts, from this new category of voices to handle them in your model. The thing is that this kind of large, first of all, large amounts of transcribed data is very rare, right? We get it maybe in Chinese, European languages, English, but not in other languages. And moreover, it's kind of an issue that the diversity of generated data is tied to the diversity of labeled data. The example I just gave between male voices and female voices. Ideally, we'd like a model where now if you just want to model a new type of voices, you just need audio from these voices. You don't need to have the transcripts that go with it. And so we saw an opportunity there because unannotated speech is obviously widely available. And what we proposed, called SPEAR-TTS, was a model that reduced supervision to the point where we could only use 15 minutes of labeled data from a single speaker. And that would allow us to generate speech in any voice. So with only a single speaker with labeled data, we could have a model that is of very high precision, but also can model arbitrary voices. And so to find the trick that solves this issue, we looked at we proposed, again, a two-stage architecture, but that is a bit different. The first one goes from text to semantic tokens. So the first model predicts semantic tokens from text. And the second one is stage 2 of AudioLM. So it predicts acoustic tokens from semantic tokens. So the first one that is kind of reading, this one requires parallel data, right? Because you need to have text and audio that are aligned to extract, to train a model to predict semantic tokens from text. However, the second one can be trained on audio-only data because it only goes from semantic tokens to acoustic tokens, and both are extracted in an unsupervised fashion. So then we try to look at something which is what exactly is captured by each category of tokens, because we called it kind of, from intuition, semantic and acoustic, but then we try to dig deeper to understand what they modeled, each of them. So the way we did it is the following. We take a ground truth audio.
This transient spring and lighting up are beautiful. A glamour.
We compute the semantic tokens, and they remain constant, right? And now, based on a single sequence of semantic tokens, we do temperature samplings of various sequences of acoustic tokens. The idea is that by doing so, everything that is going to change between the following examples is what is in acoustic tokens, because it changes when we temperature sample different acoustic tokens. And all the things that remain the same are the ones that have been specified by the semantic tokens, which is the information that doesn't change between the samples.
This transient spring and lighting up are beautiful.
This transient spring and lighting up are beautiful.
This transient spring and lighting up are beautiful.
So you can see that basically the content and some part of the prosody and the rhythm is completely specified by the semantic tokens, and the acoustic tokens instead are modeling the speaker identity. What is interesting then is that since the speaker identity is captured by the second stage, we can train the first stage on one speaker only and just let the second stage handle the multiple speaker part. So the reading part, the first one, can be trained on a small data set with a single speaker. And the second one, since it doesn't require supervision, then we can scale much, much more the training data and capture all the possible voices and recording conditions and so on and so forth without needing a single transcript. And so when we do that, there are much more details in the paper. I recommend you read that. But we were able, with 15 minutes of labeled data, to train a TTS system. And what you're going to hear here is not only the model is pretty robust with 15 minutes of labeled data, but the audio quality is not affected at all by the amount of labeled data because it's completely handled by the unsupervised part of the system.
SPEAR-TTS with 24 hours of parallel data.
SPEAR-TTS with 12 hours of parallel data.
SPEAR-TTS with 2 hours of parallel data.
SPEAR-TTS with 30 minutes of parallel data.
SPEAR-TTS with 15 minutes of parallel data.
And so for voice prompting, we can do the same that for speech continuation.
To see the signs of adolescence that made.
And combine it with a text, and then we can make a text speak in a specific voice.
And yesterday things went on just as usual.
And so as a comparison with Valley, we're able, in terms of speaker similarity, to be pretty close with a better audio quality, but interestingly, with only 15 minutes of label data. And I think I have around 5 minutes left. So I will go a bit quickly on that, but we were then interested in going from text to speech to text to music. So instead of having a text and generating audio, in that context, you would rather generate well, an audio track from a description. And so this was back in 2022, I think, 23. I don't remember. And so the idea now is, how do you get the paired data for that? So the thing is that you need captions of music. You need pairs of caption and music. This is very, very difficult to get this kind of data, much more than getting transcripts. And there is no existing back in early 2023. There was no such database. And so I go quickly on the methodology, but basically we used a joint embedding space for text and music based on a model called Mulan, which is a bit like, it could be like clip or clap in the context of audio. And the main idea is that instead of training your model to predict audio from text, because you don't have text, you embed the text into this multimodal embedding, and this multimodal embedding then becomes the conditioning to your model. So you only train on that, which doesn't require text. And at inference time, the user instead wants to provide text, and so we can compute the Mulan embedding from the text, and they can generate audio from it. So I won't have time to generate, to play too many samples, and they would honestly sound not that great today compared to Suno and Udio, which are amazing. But it was the first model to allow for such kind of natural language description of audio. Maybe okay, I'll just play one for take a bit. And similarly, thanks to the flexibility of this framework, we could also not condition on text, but we could condition on audio. So for example, what we did here with SingSong was a pretty fun project called reverse karaoke. So you take an audio and you separate, you do source separation to separate the voice from the instrumental. And now you train the model to just predict the instrumental part from the voice. When it's all over, when we... So that's the input, and the output is that. When it's all over, when we are amazed. And one thing that was interesting with this is that so we created this model called MusicRL. And we had the opportunity in early 23 to release it to the general public. It was the first generally available app for music generation. And we wanted to use that as a way of integrating human in the loop feedback. In particular, because we found during the development of MusicRL that automatic evaluation of music generation is very, very difficult. It's not reliable. Subjectivity is very important. So even when we did comparison between people in the team, nobody had the same taste of which one will sound the best. So there will be a need to integrate human in the loop, exactly like with LLM. So we released MusicRL publicly, and we were able to collect 300,000 preferences. So the trick was the following: that when people would write a description, we will generate 2 audio, and we will allow them to only put 1 trophy, right? They could not put 2, right? That would kind of force them to pick a preference, which we were advised to do because it's much easier to get a training signal from pairwise preferences rather than, for example, a scale, where you ask people to give 1 to 5 stars or something like that. And so we got 300,000 of such preferences, and we're able to use reinforcement learning to improve our model with RLHF, and that allowed us to create a newer version of this model. That's the models that are currently in production at Google, now almost 1 year and a half later, and they are consistently improving from the user feedback. So the midterm impact of what we did on codecs and audio language model, I think was significant. In particular, it's now a huge field of research where a lot of things are happening, not only in research, by the way, in research of course, but also in products. So a lot of products, including NotebookLM, Suno, many others are based on this technology. So it's also something that is used by people in the real world. And so maybe a few words, I don't know if I have 5 minutes more, but because I don't remember when we started exactly. But a few words about Moshi that we did at Kyutai. In that context, it was the first project we did in the lab, and the goal was to do real-time conversational AI. And in particular, now it's kind of become standard to have real-time conversation, but at that time, the state of voice products was Alexa, Siri, ChatGPT voice mode, not the current one, the old one. So there was a lot of latency, 3 to 5 seconds. And also they would lose all the paralinguistic information because they will not be speech-to-speech. And so our idea was to train an audio language model for real-time conversation. Another thing we wanted to crack was have a full duplex conversation. So the main idea is that most systems, to the best of my knowledge, almost all systems, even the most advanced Grok and so on, are half duplex, which means that they are based on a clean segmentation, whether the system is speaking or listening. A human conversation is much more chaotic, right? We do back channeling, we interrupt each other because we want a clarification and so on. That makes our conversations lively. I think on the column dataset, which is a dataset of people, talking with relatives, you have more than around 15% of spoken content that is overlapping. So it's a lot, and it's a huge part of human conversations. And so we developed Moshi that we showcased a year ago.
So the planet is Sirius 22. Can you plot a trajectory course to it, please?
Yes, sir.
Okay. How long is it going to take us to get there?
I've mapped it out.
Okay.
It's approximately 5 months to get there.
Okay, that's not too bad. Do you think we have all we need on board the ship to start the mission?
Yes, sir. We have everything.
And so what is interesting here is you see the model, when it knows how you're going to finish your question and start answering even before you're done, it has no issue talking over you or you talking over it, thanks to the full duplex technology. So it's just a very chill, conversation, because you don't have to be very disciplined, which is one thing annoying typically with AI, is that you have to follow a very strict discipline or the model starts to freak out. And so how we did that? Because there were several challenges that emerged. First of all, we need something that is real-time in streaming. So you cannot do the two-stage method of AudioLM anymore, right? Because you need to have semantic and acoustic tokens that are generated jointly. You also want the model to be a smart model because you want to have an actual conversation. So you need to have an LLM backbone. And you also want this full duplex ability. So I'll go very quickly on it, but the main idea is that we relied on RQ transformer, which is a hierarchical architecture, and we made a multi-stream architecture. So the main idea is that instead of having a sequence of tokens from the user and tokens from the LLM, like a typical voice AI, we model two consecutive, at the same time, and that gives us the ability to have any kind of overlap between the speaker and the system, because we have these two streams of tokens that are modeled in parallel. I unfortunately won't, I'm not sure I will have time to play another demo. Maybe one thing is that, because I think it's very interesting. So this multi-stream architecture, where you model different stream of tokens, we developed it with Moshi for real-time conversation, but it's actually a general framework for multimodal modeling and general modeling. Because now, if instead of having two streams that are the user and the AI, you have, for example, me speaking in French or me speaking in English, so parallel data for speech translation, now you have something that is real-time streaming speech-to-speech translation. Bonjour à tous. Je suis ravi de pouvoir m'adresser à vous aujourd'hui en français.
Hi everyone, I'm delighted to be able to speak to you today in French, since my phone will translate what I am telling you into English. As you can see, it is in airplane mode. It doesn't have an internet connection because our machine translation model allows for real-time voice translation entirely.
So since then, we have been able to develop, a lot of real-time application around this framework. We are publishing next week this general framework, which we call delay stream modeling, that allows for arbitrary combination of text and audio streams. And to conclude, I think what I showed today is that audio language models are very good candidates for foundation models, because first of all, you benefit from all the literature and knowledge from text LLM. Didn't talk too much about it, but we did back translation. LHF is one of them. GRPO, all this kind of stuff. You can just, use it out of the box. So which is very, very, very convenient. And they are a natural candidate for multimodality because our main approach to everything now is to discretize any kind of signal into discrete tokens, have a big vocabulary that can be shared between inputs and outputs, and then we can model on all the tasks on that. So I recommend, if you want to play more of our model, to try streaming speech to text, streaming text to speech. We are a non-profit lab, so all our output is published and open sourced, and you can find all our models on our GitHub and Hugging Face. And what's next, I think still something I'm very disappointed with, is the emergence of zero-shot abilities. In my perception, is still very, very far from even GPT-3, which means that we have not managed yet, at least in my team, to see the emergence of zero-shot abilities where you would have a model through natural language instructions that will perform audio transformation, audio translation, transcription, and so on and so forth. So I think this is going to be one of the most exciting research directions in the coming years. And I thank you very much for your attention.
Thanks, Neil. Very, very impressive demo, especially real-time translation. Shall we try to have some questions from the audience? Let's try the audio, see if you can hear from the room. Now we can have, I can repeat part. Go ahead. Can you try to be loud? So
Sure. Thanks a lot, Neil, for the talk. This was really informative.
Yeah, can you hear?
Yeah.
Yeah, so I had a question. So like in Moshi, you have like a multi-stream audio tokenization, right? Like the first stream is sort of semantic and like the others are like acoustic. So like one question that I had was that this sort of multi-stream tokenization is slightly different from a TextLM tokenization where it takes only a single stream of input. So did you observe any loss in like the TextLM's like original capabilities when you like train with like a multi-stream audio tokenization? And do you have any intuition on what are the relative trade-offs between like multi-stream and single-stream audio tokenization?
Yeah, that's a good question. So I think there are several things here. So the fact that we need several levels of tokens, that's based on the RVQ that we use in SoundStream. It's just a very scalable way to get to bit rates that are high enough to provide good audio quality, right? Because it's slow C compression, you still want to keep audio quality. The semantic and acoustic token distinction, for me, is still a huge complexity. I hate it, to be honest, but we have not managed to be able to do without it yet, right? So we tried again with Moshi to go from scratch, get rid of it, and so on, and it was still necessary. What is a bit concerning for me, and I think is a interesting question, is you also have the very same family of models you're using for audio exist in image. Actually, RQ transformer was developed for vision, and they don't need this distinction between semantic and like defined tokens, right? They just have a simple RVQ, and they are all trained with a single loss, and yet they are able to make image with high-level structure. So there is something specific about speech where I think just with next token prediction loss, you really need to bias your model to force it to predict something that is meaningful, that has semantic content. Otherwise, it can be pretty satisfied by minimizing its loss just by predicting stuff that almost sounds like speech, but is not really speech. And in that case, the boundary between something that is speech and something that is almost speech but babbling and unintelligible is very thin, right? And maybe too thin for current models at the scale that we train them. So I don't know, maybe a 100 billion parameter model trained on 1 billion hours of speech will get it without semantic tokens, most likely, I don't know. But unfortunately, we are still stuck with that at the moment.
Thanks. I think we probably don't have time for questions because we're already 10 minutes late and we want to get everyone to lunch not too late. So thanks, Neil. So if anyone has any questions, I feel like you can also ask offline. So